Welcome to the first in a series of video guides we put together for our torque, drag and hydraulics modelling software TDH. These videos are designed to highlight the benefits of the software and to provide users with hints and tips on how to model various common engineering scenarios. TDH is designed to bridge the gap between the office and the rig, allowing engineers to proactively manage drilling performance on the basis of what's measured, because as the old saying goes, what gets measured gets managed. We are interested in using the models to guide our next steps, to reduce risk and improve performance, and TDH makes this easy, as you'll see throughout the series. But first, let's look at a scenario where we need to decide how to run a string of 9 5/8 casing in an extended reach well. We're going to look at two options, running the casing conventionally to see if that'll work first, and then we'll look at floating it as another option. I'm in the selector screen, the SC button on the left hand side. From here, I select my first scenario, the conventional casing option, then click on WP, which means well path, to take a look at the trajectory. You can see I have an S-shaped well with a long 12 1/4 inch hole at high angle, with my 9 5/8 casing set at around 4,400 metres. Clicking on the DS button for drill string, let's look at our running string. In this case, you can see we're running in hole with two types of 9 5/8 casing. A longer section of 47 pounds per foot and a short section of 53.5 pounds per foot, extending from surface to round about 600 metres. Now let's go to the analysis view, AN on the left hand side, and look at what's happening when we run the casing in hole. We're looking at a hook load broomstick chart. In order to get some useful information out of the chart, we need to include our block weight, which you can see from the data is 42,000 pounds, and we'll add this as a limit because if our slack off weight drops any lower than this, we're going to have to start pushing the casing in hole. So let's go ahead and add this onto the chart. We are expecting to see a friction factor of 0.6 from our offset well review, and based on this, we'll be able to run the casing to around 3,100 metres before we start using block weight to move the string. We still have another 1,400 metres of pipe to run past this point, meaning as it stands we won't be able to get the casing string to setting depth conventionally due to drag in the hole. There are a few things we could try to reduce the friction factor, perhaps use oil-based mud, lighter casing if possible, or perhaps we could rotate the casing to break the static friction and convert the axial drag into torque. So, I select Surface Torque from the drop-down menu below the Analyze button to see what this shows me. Not much is the answer. Looking at my makeup torque, which will be the black dotted line, you can see that all the friction factor load lines intersect with the makeup torque line before casing point, and that only in the unrealistically low friction factor case, the load lines also intersect with the operating torque limit well before TD. So, in summary, we can't rotate the casing. Taking into account we can't rotate the string past 1,700 metres and run out of weight at 3,100 metres, we're not running the string conventionally. Now let's switch to the floated casing scenario and check the inputs there. As you can see, we're using the same casing string, but this time we will define flotation intervals in the input box to the right of the drill string view. We have 3 flotation intervals in this case. The first one is a 47 metre shoe track filled with base oil, followed by an air-filled casing interval, followed by a casing interval filled with mud above the flotation collar. Now let's analyse the scenario with the same input parameters and check the results. Compared to the previous simulation for the non-floated string, our results now show decreased drag while running the air-filled casing interval and increasing hook load once we start to run mud-filled casing in the upper part of the wellbore. The actual values, shown by the blue triangles, are plotted on top of the calculated load lines. This shows that there are only a few instances where small amounts of block weight was needed to push the casing in this configuration. Thanks to TDH, we were able to optimise the fluid intervals for our client, achieving a trouble-free floated casing run. The actual values followed the expected trend neatly, validating the algorithms and formulas used in the model. Finally, we'll go into the report view and output this casing run into the end of well report. Now, while we're here, let's check if we could have rotated the casing string while floating it in the hole. Looking at the surface torque template, there you go, The model torque values for the floated casing string are quite low, and we could have easily rotated the casing should we run into trouble on the way down. As you will have seen, it's quite easy to manipulate the software, producing meaningful, well-presented, and more importantly, auditable results with only a few clicks of the mouse once you have your scenarios set up. We will be putting out a few more short videos over the next few weeks, so if you have any requests, please let us know.